of a manifold. And we will now talk about the formal definition of it. So what is a manifold? And this is the definition. A manifold M and let's say this M is called m-dimensional manifold. A manifold M is an m-dimensional space or a generalization of a space, or you can say it's a topological space, whatever. So this is an m-dimensional differentiable okay, let's call just M. Okay, if M, which is m-dimensional, is called a differentiable manifold if the following axioms, or the thing that we are calling M, satisfies the following axioms. The following satisfied. Number 1, M is a topological space. 2, M is provided with a family of pairs ui phi I. And what are these ui and phi I? These are this set of ui's is a family of open set which cover M. That means the union of all ui should give you M. Then phi I is called a homeomorphism, is a homeomorphism from the open sets ui on M onto an open subset u prime I of the m-dimensional Euclidean space. And this is what we mean by a local flatness that we discussed in the previous lecture. So on a manifold we can define this sort of a homeomorphism. And then finally, the last axiom that a manifold has to satisfy is that given ui and uj, the open sets, such that if ui intersection uj is not null, then there exists some sort of a map psi ij defined by phi I, phi j inverse from phi j ui intersection uj to phi I ui intersection uj is infinitely differentiable. And the following picture will make you more clear on what this fourth condition actually does. So let's try to draw a picture first. Let's say this is our M, the thing that we want to call a manifold, and this is one of the open sets, let's say UI, and there is a open set uj, and this is the overlapping region. Now, according to our axiom or definition of the manifold, we can define some sort of homeomorphism phi I that will take elements from this set UI and map this into the r-dimensional Euclidean space as some portion of another open set. Let's call it UI prime, and from here you can define another homeomorphism, let's say called phi j, and this will map it like this. Note that these highlighted areas like this, they represent the overlapping region in the manifold. Let's call that uj prime. And what this psi ij does is the following. So if you write the definition of psi ij, what it does is that if you start from this coordinate system, let's say, let's call this the primed coordinate system with some x prime y prime for our convenience, and let's say this is x and y. This psi inverse takes psi j inverse takes elements over here, that means these guys on the overlapping region. It maps it to uj, where it will belong in this overlapping region, and from there you can use the homeomorphism phi I to map it over here. So technically this psi ij is behaving like a coordinate transformation. Transformation for the, let's say, points in the overlapping region in M. Okay, so this is what it means, the condition number 4. And if you can recall, in the first lecture we required that we need more than one charts, and even though a point can have different coordinates on different charts, and if two charts overlapped, we said that we want some sort of a smooth transformation that we all know in real variable calculus as a coordinate transformation. This is the version of that thing when we are discussing about manifolds. Now, a few things have been left undefined, and so let me define that pretty quick. Is that the pairs of the open sets and the homeomorphism are called charts, and this is what I've been uttering for a few times in the past lecture, and this is the formal definition of a chart. And this family of charts is called, okay, let me write it down. The family of charts is called an atlas. The open sets are called coordinate neighborhoods, and the homomorphisms are called coordinate functions. So what can happen is that you can take any point, let's say P belongs to M. Then if you use this map, let's say some phi, I'm getting rid of the index, and it returns to you some x mu of P. You can even call this map a coordinate as well. And the map I used over here, this is just a identity map. So in some sense you can also call this phi as the coordinate itself. Okay, and if you use the identity, if we use phi as the identity map, we write the coordinates as x1, x2, x of n, let's say x of m, sorry. So what we note is that, so this is a note, or you can call it a remark. Note that the point P exists independently of the coordinate systems. And it is up to us how we want to assign that coordinate to that particular point. Okay, so what I mean by that is that I chose the identity map, let's say, that I showed you over here. You can choose different maps. Instead of identity, you can choose, let's say, some map that takes every point or the points in the manifold and maps that point. Instead of m numbers, you can map it, let's say x1 squared, x2 squared, and so on. So the most convenient thing that we are familiar with is that the identity map, where you take a point on the manifold, and when you use the homomorphism, it gives you some m numbers in Rm. Okay, so again, the condition 2 and 3 tells us about the local flatness, or so to say, they're locally Euclidean, and if we have such ui and uj, which we definitely have on a manifold, if we have a configuration like this, then if there is a point P over here, that means P belongs to ui intersection uj, then we will have two coordinate systems attached to it. And by axiom 4, this transition from one coordinate to another should be smooth. And since phi 1 assigns m coordinates to P as x mu, let's say, so let me draw the picture again and write this for you. So let's say this is the overlapping region, and this is some point P. So what I'm saying is that we see that UI UJ intersection is not null, right? So for this P belongs to UI intersection UJ, we have two coordinate system attached to it. One can be called as, let's say, phi, another one can be, let's say, psi, or you can say phi I, phi j. It's up to you. And we are saying that the axiom 4 thing tells us that the transition between these two coordinates should be smooth, right? So say the coordinate phi gives or maps my point to coordinates, let's say, denoted by x mu, phi I, and phi j takes that point and assigns coordinates y mu. And we're saying that, or we require that the transition between x mu's and y mu's should be smooth. And if you write this out mathematically, that means if you say that okay, these are smooth and all that stuff that we want to do, if all these are satisfied, then you can write x mu in terms of y. And you can also even write y news instead of in terms of x. Okay, and this is indeed the coordinate transformation functions, and this is just the explicit, to be precise, this one is the explicit, and by explicit I mean the coordinate form of psi ij that was defined by the functional composition of phi I and phi j inverse 1. And by saying that this coordinate transformation is smooth, we have differentiability in the same sense of the ordinary calculus. And this coordinate transformation function, it is differentiable, or so to say, it is smooth with respect to all y of nu. If this is differentiable, then, or so to say, if it's smooth, then it's differentiable with respect to y, all y of nu, that means all the y coordinates. Okay, and all these conditions tell us that once we assign a coordinate to our point of interest P, which belongs to M, then the coordinates are assigned in such a manner that no matter how we move in M, the coordinates we use vary in a smooth manner. That means it's always possible to go from one coordinate to the other. And that's why earlier I said that all coordinate systems are equally good for our working purpose on a manifold. And the reason we want these smooth transitions is that, again, I discussed this before, so let me remind you, if these transitions are not smooth, what could happen is that on one chart you may find a function which is differentiable, but now when you are going from one chart to the other, what you are doing is that you are changing your coordinates, right? And if your coordinate transformation is not smooth, it may happen that the function that was differentiable on the chart that you started with is not differentiable anymore. So that's why this smoothness condition is necessary. Okay, now that we saw some definitions and we talked about some formal things, what we can do right now is that we can jump into some examples. our manifold. So